Okay, so this would be a non-chain rule way to solve this problem. You can also do this with sine 3x, sine 4x, and so on, but you'll find it gets very, very difficult very, very quickly. Okay, I'll just get you started on sine 3x, and I think you'll appreciate the chain rule in the end. Okay, so let's do this one. Let's let y be sine 3x. You would say, do I know any identities for sine 3x? Probably not. So what you would do is you write this as sine of 3x plus x. I meant to write 2x plus x. Write it as sine of 2x plus x. And then you could use one of your like angle sum rules where you go sine 2x cosine x plus cosine 2x times sine x. You probably remember that rule, right? If you have an angle sum, you just do cosine of the first angle, cosine of the second angle, plus, and then that under first. And then this can be written, this first part here can be written as 2 sine x cos x. And we also have a cos x here, plus, and then this cos 2x, man, that thing can be written 3 different ways. That can be written as 1 minus 2 sine squared x. That can be written as 2 cosine squared x minus 1, or cosine squared x minus sine squared x. 3 different versions of that thing. So I think I'll use the 1 minus 2 sine squared x. So if I distribute that with this sine x here, it would give me this problem. Sine x minus 2 sine x sine x sine x. Wow. So this would be a way I could do the problem. I could then pursue the product rule and finish this up. By the way, if you're wondering what the product rule is for 3 multiplied functions, u, v, and w, it's u prime v w plus u v prime w plus u v w prime. So you just extend that product rule into three terms. Okay, so, but you could do that here. But you can see this is not going to be a preferred way to handle the problems. What if we were doing sine of 100x? Really? You're not going to do that, right? Okay, so let's go back to this problem here, and let's talk about how it would be handled with the chain rule. Okay? So if you're going to do this with the chain rule, you think totally differently. You want to look at this as the composition of 2 functions. Okay, so I'm looking at this and I'm saying, I see 2 functions. I see the function sine, and I see the function 2x. And what we're looking at here is just the composition of it. It's f of u. You know what I mean? It's like f with u plugged in it. Sure, if you plug this in right there, you do get the original function. Okay? So I'm thinking of it as 2 functions, f equals sine x and u equals 2x. I know the derivative of both of these things, don't I? I know the derivative of sine x, I know the derivative of 2x. That's not a big deal. Maybe there's a way to kind of link those together to get my answer. Okay, so here's how it works. You want to think of the chain rule this way. You're going to take the derivative of sine 2x as if 2x were a variable. And then you'll take the derivative of 2x with respect to x. This is the basic idea. Okay? It's really not very hard. It takes a little to get used to. So what was the first thing you probably noticed about this problem? It is a sine. So you would just apply the rule for sine. What is the derivative of a sine function? Cosine. Now, there's no reason to change the angle. If the angle's 2x, the angle's 2x. So this just comes out to cosine 2x. See? Sine 2x has derivative of cosine 2x. If you're differentiating with respect to 2x. Okay. Now we're going to take the derivative of 2x. That's simple enough. What's the derivative of 2x? 2. So the answer is 2 cosine 2x. This is the same answer I got when I did it with identities, only this is a lot faster. So the idea is we have an outer function and an inner function. First we look at the outer function. We say, oh yeah, that's a sine, so the derivative will be cosine. function and you say, oh, that's a 2x, the derivative is 2. Then you multiply them together. Okay? All right, with that method, we can do d dx of sine 3x much, much faster. So just pretend that 3x is your variable and take the derivative of sine 3x as if 3x were the variable. And then multiply by the derivative of 3x with respect to x. Okay, so the fact that it's a sine means it differentiates to form a what? The derivative is a what? Cosine. Okay? Cosine 3x. What's the derivative of 3x? 3. So you mean to tell me that the answer to this problem is just 3 cos 3x? Yes. It's that simple. So the answer to the previous one was 2 cos 2x. The answer to this one is 3 cos 3x. Okay? All right, let's do another one. What if you had d dx of sine of x squared? D dx of sine of x squared. Well, we have two functions. There's a sine and there's an x squared. What's the derivative of sine? We said it is cosine. Don't change the angle. Just write cosine x squared now. It was sine x squared, now it's cos x squared. Now look on the inside. What's the derivative of the inside part? 2x. Multiply that on. U is done. That's the answer. How about this one? How threatening is this? Not very threatening. Because we know the derivative of tan. Do you guys remember it? Sec squared, right? So you just simply write that, right? Sec squared. Don't change the angle. It's still 3 minus 5x squared. Multiply on the derivative of the inside. So what is the derivative of 3 minus 5x squared? Negative 10x. It's almost like I'm ignoring the 3 minus 5x squared at first, but then I caught it later. You know, I was just pretending it was not worth taking the derivative of that. But I actually did take the derivative of it, I just tacked it on at the end. Okay? Let's try this one. d dx of sine squared x. Not the same as sine x squared, right? So it would probably be helpful to see this written like this. D dx of sine x squared. So I've changed my mind about this problem. The first thing that catches my eye is not the fact that it has a sine. What catches my eye is it resembles x squared. It's something squared, right? So that's actually going to be my first thought. If this is a composition of two functions, they are the functions f equals sine x and g equals x squared, but it is g compose f that I'm looking at here. In other words, the outer function is clearly the square. So that needs to be dealt with first. So what is the derivative of anything squared? 2 times that something, right? So you would bring the 2 down as a first step here. Changing the power to a 1. That's what you do with x squared, and that's what you do with sine of x squared. So we have basically bringing the 2 down. The sine of x squared is now simply sine of x with a first power. And now we look at the inside and say, oh yeah, there's a sine x. What's the derivative of that? Cosine x. There's the answer. Okay? How about this one? The derivative of sine cubed x. I'm going slow because this is brand new for some people. Okay? If you write it like this, you realize, oh, this is like an object cubed. So what's my first step? Bring down the 3. Sine x no longer has 3 powers, it only has 2 powers. Now I look at the inside and say, oh yeah, there's a sine, and multiply on the derivative. See? This allows us to do problems that would be completely impossible, practically speaking, if we were doing just straight identities. You could do a 100-way product rule, I suppose. you would get a polynomial with probably 100, 101 terms. You would have to collapse it back down using identities. But you know what the answer is going to be in the end, in the simplest form? 100 tan to the 99x times secant squared x. Why? Because you bring the 100 down, you change it to a 99, then you say, oh yeah, there's a tan there. And then you take the derivative of that and tack it on at the end. Beautiful rule, super powerful. It reminds us of de Moivre's theorem, you know, a little bit, where you do like 5 plus I to the 10th power, and it's like, nobody wants to FOIL it, but if you put it in polar form, it's a snap. It's super easy to do. Maybe you remember doing that. The chain rule always reminded me of de Moivre's theorem. It allows us to do super high powers very, very easily. Okay, it doesn't only work with integers, it works with fractions too. So namely, roots can be written as powers. Powers can then be treated in this way. I'm going to handle the root stuff more tomorrow because there's some funky factoring if you're doing a second derivative of a radical composite function. So I will help you with that tomorrow. But I did pick a couple more little examples here, but I have to take a peek at them because I don't know where they work. Give me 1 second. Ah, yes. Composite of trigs. So what would happen if you were asked to do, let's see, ddx of tan of secant x. Okay, this is not tangent x times secant x. This is tangent of secant x. So secant x is our angle. How strange. Okay, but that's what we have. So what catches your eye first about this problem? Do you see it as a tangent something problem, or do you see it as a secant something problem? You should be looking at the outer function first. So you should say, ooh, a tangent. Okay. Now you ask yourself, what is the derivative of tangent? Sec squared, right? Sec squared. Okay, so the derivative of tangent is sec squared. Don't change my angle, please. My angle is secant x. Keep it. Okay? No, really, a lot of students change that to an x. My angle is secant x. Leave it alone. Don't touch it. Okay, now you look on the inside and say, oh, there's a secant there. What is the derivative of this part? Sec x tan x. Secatan. Go to the beach, right? Do you guys see what I did? I took the derivative of tan first. That's sec squared, but I left the angle as secant x. Then I looked on the inside and said, oh yeah, there's a secant x on the inside. Then I took the derivative of that and tacked it on at the end as a factor. It gets multiplied on. Okay, let's switch it around. Let's put the secant on the outside and the tan on the inside. Okay, just for variety's sake. So last time we viewed this problem as a tangent first and then a secant, but on this one we have to first view it as a what? Secant, and then the fact that there's a tan inside. So just ignore the tan right now. We need the derivative of secant. Okay, so what's the derivative of secant? Go to the beach, right? So it's sec tan. Don't change my angle. What's my angle? Thank you. Oh, except I didn't leave enough space to write it. So I meant to do lots of space here because I have to put a little tan x in here. And now I can multiply by the derivative of the inside, which is the derivative of tan x. So what's that? Secant squared x. Do you think this is confusing? Not if you understand what the chain rule is asking you to do. Chain rule asks you to ignore the inner function, differentiate as if the inner function was your variable, keep that variable as your variable, then multiply by the derivative of the inside. Yeah, it's fine. I mean, I'm sure there's some weird way to rewrite this, but frankly, I don't know what it is. You've got two different angles going on. You've got tan x as an angle, and you have x as an angle. So those can't be easily combined, right? So, and the parentheses are really important, right? Because you don't want it to say tan x, you know what I mean, right? here, like if you wrote tan x, I have to mark you down. This is tangent of tangent x, whatever that means. All right? So just let it be what it is and follow the rule. Okay? All right. Okay, let's talk about motion for a minute. So motion is going to show up every chapter. What we did in that warm-up today is tangent lines, normal lines, that sort of thing. It shows up in every chapter, and motion is going to show up in every chapter. And later on, we're going to add to those familiar AP topics as we go, okay? So we need to do a motion problem here. So here's what I picked. An object is moving along the x-axis. Such that its position x of t is s of t. Okay? Find the velocity function v of t. Okay, so my function that I'm choosing is t times sine of pi minus t over 4. Let's do pi plus t over 4. Okay? This is a position function. If you give me a time, I can tell you where the object is. What is the physical phenomena? Like what's going on? I have no idea. Something is causing this particle to move. For some reason, this is how you calculate its position. So don't think too much. Just go with the givens. Alrighty? For example, if time is 1, right, you plug in 1 and you can tell where it is on the x-axis. So it's kind of like what we did yesterday. It's an object just moving around on the x-axis. It's probably doing some kind of a back and forth motion. I don't know. Okay? If time is 10, you're going to get a bigger number than if time is 4. So I think what's going on is it's like oscillating back and forth, but it's also increasing its amplitude. So all that's very interesting, but you can get away with a lot not even understanding that. I want the velocity function. How do I find the velocity function when I'm given the position function? Just simply take the drift. Okay? So velocity is going to be s prime of t, or you could say ds dt. Right? Okay, so what do you see first in this problem? Yeah, I see that it is a product rule, first and foremost. Right? The first thing that caught my eye was this is no simple problem. I've got t and sine of yada yada t in one problem. That means I have a product rule situation right off the bat. So I'm going to set up my 4 parentheses now. For the product rule. And this will be like my little u and my little v. I guess my independent variable is t, not x, but that's okay. Okay, so first would be, I'll do it in this order. I'll do u prime v, sorry about that, and then v prime u. I like to do it in that order. So let's do u prime v, and then v prime u. Okay? So what is u prime? U is simply t. You can think of that as x, you know. 1, right. Okay, so that's just simply 1. What is v? Well, just copy and paste. So just stick that in here. Plus, v prime, no fun. Let's come back to that. T is the u, so we can put that here. And I'm going to need a little more space for that v prime. That's going to be the ugly part of the problem. Okay, so I'm going to give myself a little more space. U is so simple. Okay, so what is v prime? Well, see, v prime requires me to use the chain rule. So how do you see this? Sine of something, right? Okay, so we know for a fact that it's going to come out to cosine of that same something. Okay, so it'll be cosine of pi plus 1/4 t. Don't want to change my angle, remember? If the function is sine of blah, 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 then you start with writing cosine blah, blah, blah. Okay, now we look on the inside of that, and we say, what is the derivative of pi plus 1/4 t? Simply 1/4. Correct. The pi is a constant. So here is your answer, and this just begs to be rewritten nicely. So we shall do that. So we have sine of pi plus t over 4 plus, and then right here there's like a 1/4 t. I'll put that in the front. And then there's a cosine of pi plus t over 4. And this is your velocity function. It will tell you how fast and which way the object is moving if you give it a time. Just for kicks, let's write down the speed. The speed would be the absolute value of that. And I cannot think of a way to simplify this at all. Okay? So I have to write all this nonsense for a speed function. But who knows? Maybe they'll ask an AP test for the speed function. And you don't want to leave it as the one I boxed. You want this one here. Do you suppose we could do acceleration? We could. Would it be fun? No, not fun anymore. Speed was a blast, but acceleration is a pain because you have a sum of two objects. The second one requires product rule and chain rule again. Okay, so that's the end of the lesson.